See, can everyone out there hear me?
Yes.
Oh, wonderful. It's great to be here. Thanks so much for the opportunity to join you guys, even if it is remotely. My name's Ryan Smith. Up here with me, or up here with you actually, is Jeff Martz. And you guys probably had the experience of seeing the demonstration yesterday. So what I'm going to talk about is all the software and the innovation, the tech that went behind building that vehicle and what's actually running on that. So we're going to talk about how we get into mines with unmanned vehicles. And just to kind of give you a start here, let's see, is that, there we go. So I run the Robotic Gnome Lab at Fort Lewis College. We do basically putting robots into harsh real world environments and pushing out persistent autonomy. So what we're looking for are systems that operate for long periods, no human intervention, complex dynamic environments. And the focus in my lab for a long time has really been on the water. But because of the things that we see in the water and the complications that we have, we're actually expanding to a lot of other environments that I'll talk about today. So one of the reasons, well, the reason that I can't join you is that I actually took a new position last week at Oxbotica, and I'm over here in Oxford, UK, working on some autonomous cars. So last week I was up in London. You'll see the picture of Big Ben in the back there, running some on-road cars. Yesterday and the day before, I was out in a mine. You'll see there, we've got an off-road vehicle doing some autonomy there. And we're looking at how we can actually use the same autonomy on multiple different platforms. If you get a chance, check us out at oxbotica.com. I'm still affiliated with Fort Lewis. I have a 10% appointment there, 90% appointment here at Oxbotica. So if you do the math, that's about 150% of my time taken up with autonomous vehicles. So what we're looking at here, and the big problem that I'm trying to solve, kind of my 20-year goal here, is if we have a feature that's out in the ocean, say an ocean front, how do we sample this guy? And what we're looking at is basically taking an aerial vehicle or having some observation or some a priori knowledge of what that is. And then how do we actually look at that feature, maybe predict that feature, and plan with an autonomous vehicle to give it enough information. Oops. Oh, come on. Come on, internet. To give that enough information to do onboard autonomy to sample a feature in the ocean. And for those of you that are a little unfamiliar with autonomy and operation in the ocean, we have a couple of constraints and some challenges. So we don't have any GPS. Once we go underwater, we basically lose localization from any GPS. Vision is really hard unless you're in the top, probably 10 meters and you have some light, so you're in the euphotic zone. Communication is really, really low. We got to use acoustics, so we're on the order of bits per second. I don't know if any of you guys think in that kind of term anymore, but like a megabyte is about 100,000 bits. So just think about that a little bit. We're going 100 bits per second, so maybe 56 to 100 characters per second. We can't see the vehicle when it's operating, large disturbances with currents, and a lot of times the unexpected does occur. And so you can kind of see the analog here between operating underwater and operating in restricted environments, say mines, caves, or the underground, the terrestrial underground as well. So some of the stuff that we've done, I'll talk a little bit about the tech behind what's going on, which is related to water, as you might understand. In this talk. So what we've done is looking at ocean fronts, we're trying to create a spatiotemporal field. And so we partnered with the crew up at Lake Nighthorse, and we're able to turn on the pumps there and create a river plume. We've taken a lot of data of this plume. We've done some Gaussian process regressions, and we've basically been able to estimate and interpolate what this plume looks like, and you can see the slices down there. But the really cool thing that's come out of this is by applying convolutional neural networks, or as commonly called deep learning, we're able to take those data there on the left, and we're able to predict a 3D model of the plume only from an image from a UAV or a quadcopter flying above. So we take a picture on the left there, and then we can predict what's going on in 3 dimensions. Now, what this does is allow us to have a prior in order to basically give the vehicle an idea of what's going on, and then we can run some lower level autonomy to actually servo around that and optimally sample without having like heavy on the exploration piece. We're actually exploiting what we know about the environment from a very sparse model to begin with. So we're using some pretty heavy tools here, but we get a big return. Now, we've applied this in Portugal off the Douro River. You can see we've taken some images based satellite on the left and from a UAV on the right there, and you can see the plume edge. This is a salinity plume, but it works the same as turbidity. It's just a different ocean parameter. And you can see we can put an underwater vehicle out there, and we can actually servo on the edge of that plume, and we can track that. You can see the edge of the plume in the data that we show there on the right-hand side, and we've plotted that over on the bottom left there. And you can see that's where the front actually is when we're looking around there. So we can just tell the vehicle, here's where we last saw the plume, and it'll go out autonomously servo on that edge. So then what we come back to then is, how do we know where those data were? How do we localize? How do we understand and navigate through the water? And my lab has created what we call augmented terrain-based navigation. Now, if you think back around the 40s and 50s with guided missiles, what we had is terrain-based navigation, where when you're flying over a terrain, you know the topography very well, you measure your altitude, and you can back propagate where you were based upon the topography that you know. So what we've done is we've created an analog for the ocean where we don't use topography, but we use ocean measurements, because in oceanography, patches of water tend to stay together. And we can actually create a topography scalar field or a topography map just using ocean parameters. And so we use a weighted linear combination of all 8 of our ocean parameters that are collected on the vehicle. These are cheap, they're really easy to collect, not very power hungry. And we can create a simple scalar field. Through this scalar field, what we do is we do an interpolation over that field, normalize all the data, we run it through a Dirichlet distribution. We do some whitening, which I'm going to talk about in a minute, which is basically decorrelating all the data so we can normalize it individually. And we do a global autocorrelation to try to actually increase the bumpiness here. So we get the autocorrelation as small as we can through a big optimization, a lot of compute going on here. And essentially what we get is every trajectory through the ocean then is unique, or the actual space that we're looking at. So now what we have is a very unique map of the ocean, and it's very reliable and robust. And I'll show you how robust that is. We can actually go out, this is off the coast of Santa Catalina Island in California. With our underlying map, we can run a trajectory, and if we don't do any whitening, which means basically decorrelating each of those ocean parameters to be individualized, which is a big no-no in oceanography, but in autonomy, it really works well. We get about 4.7 meters of error over a 150-meter trajectory. If we apply our whitening technique, which is kind of our special sauce that we figured out, we can actually get an error, an RMS error over a 150-meter trajectory of about 1.1 meters. Now that's pretty amazing because it's better than GPS. Now we're ground truthing against GPS here, so there's a little bit of error that's going to be in there, but to within 2 meters, that vehicle knows where it's at. Now here's the cool thing. We went out the next day. We didn't even make a new map. We just went out the next day, used the old map. The tide has changed. It's a different time of day, and we're running a running in the water there. Without the whitening, we're about 16-meter error, which is actually pretty good for water anyway. But when we apply the right whitening, we come back to about 1.2 meters of error along that trajectory, about 150-meter trajectory. So it's actually really, really good. So we're robust to changes, and the whitening actually helps us here because the water patches stay together. And without the whitening, it's assuming basically things are moving in a different way than they actually are through the distribution process that we run. But here, when we whiten and decorrelate, we can actually get a really good localization estimate. Now, when we throw the vehicle in the water, it has no idea where it is. There's no GPS. All we give it is we give it a compass heading, and we give it the nominal velocity that it should be traveling. Within about a half a second, it's able to localize in the map, and it's able to hold that localization to less than 2 meters for over 150 meters of that trajectory. So again, we throw this guy in blind. We use no motion model, and we're able to localize to that map really quickly and hold that localization over the whole trajectory. So one of the coolest things I think we've developed in the last month, and this is hot off the press, is that you would think that if you make a static map here, things are going to change. It's the ocean. It moves all around. So what we've done is we've actually incorporated this ATBN into a dynamic SLAM framework. So SLAM is simultaneous localization and mapping, for those of you that don't know, which means when you drive around in your car, you know, a lot of autonomous cars, Waymo and Toyota are doing this right now, is using SLAM to do everything. They run around with a camera and, don't go there yet. And they take a bunch of pictures, and when they see the same thing again, they know that they've gone in a circle, really similar to how you navigate in a new city. If you look behind me, you'll see Big Ben. It's all under construction right now. But when I walk around London, I see Big Ben. I go on a little tour and I come back, I see Big Ben again. I know I went in a circle, and I know I'm not over on the other side of London. So we can do the same thing with our imagery here, which our imagery is actually ocean parameters underwater. So we have this feature-rich environment, which acts like our camera, and we can slice this up into the different layers. So temperature, salinity, dissolved oxygen, pH, turbidity. And in each layer, what we look at here is we look for landmarks. So let's just say we pick a temperature of 11.2 degrees. And for that temperature, what we're going to do is we're going to tell the vehicle, you're looking for 11.2 degrees. Similar to when you walk around a town, you look for Starbucks. I don't know if you do this and count Starbucks like I do around town. But sometimes you can get up to like 30 or 40 within 3 blocks. It's just amazing that they can support that. But anyway, here you can see that there's a cluster of 11.2 there. So what we do is every time we go through, we mark those. And then we do a reinterpolation of our maps. We have an old map. We go back out in the old map. We look at where that 11.2 might occur, where we think we saw it before, or where we actually re-record it. And we do a subtraction here, and we look at the variance. And now, by looking at the variance of the difference between where it was before and where it is now, we can actually see what had happened around there. And because water tends to patch together and stay together, this variance is a robust parameter for dynamic events. And so what you get here then is actually, when you pull that apart, you can see now the whole background fades away, and we have very distinct landmarks. We can actually use these to navigate and localize. So what's interesting here is now we have a map with landmarks in it that are allowed to move. And we know how they're going to move because we looked at the variance, not at their exact location, or tied it to a map parameter. So now just think about this. You want to go to the grocery store, and the grocery store moves around in space and time. With this, I can predict where that's going to be. So now I can plan a route to where that grocery store is going to be. Or if I see the grocery store, I know where it should be at that time, and I can localize and know where I am relative to that. I don't know if we're actually, as humans, as good as that right now, but this is actually really cool. I've got a student, my PhD student in Columbia, is working on this, and I'm really excited about this work. So that brings us to the big question of what is a map? And especially when we look at underwater environments or underground environments and things like this. And so this is where we're going to transition to the application of this tech into some other areas, because we don't have GPS. How do we communicate between robot and person as to what's going on? And one of the things that I've been looking at lately are what we call topometric maps. So the maps that you're kind of familiar with and looking at like a regular sheet are metric maps. They have a metric space applied to them. So there's a distance metric on top of that. So when you look at a map, it's relative. You have a scaling parameter, and you know that the distance from Durango to Denver, or Durango, let's say Durango to Silverton, is 54 miles. You know what that distance is. You can measure that and see that. You see that basically in that on the right-hand side there under the strip map A. There's topography, there's distance. We know what curves we're going to take. Um, topographic maps, or maps based on a topology, don't have any metric information in them. So there's no distance associated with them. And so how do we use these maps in order to help us out? Well, the Marshallese Islanders, way back when, the wayfarers, used stick charts. Little kids used to sit with these maps that on the left-hand side in the black there and play with them with their fingers. And they'd learn the wave patterns out in the ocean. Then they'd go out in their canoe and they'd lay down in the canoe and they'd feel how it oscillated, and they could tell where they were. Sorry, this is jumping around here. Come on, here we go. They could tell where they were based upon how the canoe oscillated. Now we've resurrected a lot of this navigation technique and we've put it in on some scaled down boats, and we found we can actually do it with a cheap IMU and a little computer extremely well. So we're applying this navigation to our open ocean vessels now. But now what comes down to underground navigation here are these strip maps, which I think are pretty great. So regular maps look at like this map M0. And you can think of the oldest strip map I can think of, and I'm a pretty young guy. So are the AAA triptychs. Anybody out there remember those? You wanted to go somewhere, you called up AAA, and you got that flip book of the map. Well, they were all in a line, and they didn't have the compass rose oriented correctly. They all just made you go straight, but you were going like from Michigan to Colorado. You never went in a straight line. You went all curvy, but they just sectioned that map enough so it looked like you were always going straight. The subway system in Washington, D.C., right there on the right-hand side, that's a strip map. You know the subway doesn't go straight, but it tells you the order of these stops with some idea of which ordering they go in. And this is where the application to the mines comes in. So when we look at these strip maps, they're very good in their theoretical construct, but they also have an extremely rich experimental application. So when you go from like a strip map A, which has a lot of topography, a compassed rose, a lot of landmarks on it with a lot of information, which humans can parse, but a computer cannot very well, we can actually reduce that down to a topographic map, which is down there in the lower corner of F, which is just a straight line, which is totally landmark based, which has no distance metric or orientation on it. And I'll show you how this applies here. So when we go into, So when we go into the mine, we're actually using, for our navigation stack, we're using a strip map. The robot actually has no idea that the mine is going to turn left, turn right, go up, go down. It actually is just looking and recording landmarks as it goes and saying, I should see this one, I should see that one. And what you're seeing there then is the old way we used to tell directions. Take a right at the McDonald's, go down the street about 3.5 blocks. If you cross the railroad tracks, you went too far. Well, if you cross the railroad tracks, what do? You turn around and go back. So we've programmed that into the vehicle in the mine. When it drives along, we know we can't go outside of that tunnel. There's no way. So why try to model the tunnel with any complexity about more information than it really needs? We're going to model it as a straight line. And as it goes by landmarks, we're going to record those landmarks to be able to navigate further back out as we come back out. A advanced way, and we actually use an S1 strip map, which is topologically equivalent to a circle. So when we drive around the edge, when we drive around the edge of a plume, we're actually seeing the turbidity or the salinity on one side or the other. And when we complete that circle, the turbidity should be either all outside or all inside. And then we can reference every localization to that, and we don't have to have an absolute map. So now going into the Gold King mine, this is really where the application comes in and what we've done. So thank you for sitting through the tech a little bit to get to this application, because this is really cool. So right now the Gold King looks like this. We had some students up there about a month ago or so. You can walk in this reinforced area, and then we've got about a 0.6 by 1 meter hole. So the robot size has to be restricted. And then after that, it's a couple of bulkheads and kind of some unknown stuff. So as we go through, what you're looking at is we've got a lot of water. you've got a lot of what I call butterscotch pudding. And so boats probably are not a great idea because there is some raised sludge that you'll get caught on. So a pure boat's a bad idea. Terrestrial robots won't work. They'll just sink into the ground. Chuck Norris may be back there, so you got to worry about him. We don't know where he is right now, so you got to watch out for that. You've got water coming down, large wind gusts, and you know, we tried quadcopters originally, like aerial vehicles, but the flight time was just too short to really provide the proper information and do the right data collection for what needed to be done. And you run into this diminishing returns thing of, I need more payload, I need more batteries to run the lights, to run the cameras, to run this. But then the batteries cause extra weight, the payload causes extra weight, you need more batteries, you need more time. And really you come into, you only got about 12 minutes. So you got to fly at about 75 miles an hour if you want to do anything. And that runs into problems as well. As you can see, a controller's got to go really fast. Now, DARPA's looked at this problem, and for the past 2 years, they've had what they call a Subterranean challenge. A good friend of mine, Tim Chung, runs this program. It's a $50 million program, basically supplying colleges and companies with funds to investigate the urban underground, tunnels, caves, things like that. So they just had a challenge a couple, maybe a month ago, I believe. And so here were some of the things that you see for what they're doing. And I just want to say, every mine that I've been in has had fluorescent lights down the side of it. I don't know about you guys. And it has all these nice little visual cue landmarks, nice track down the middle. Most of them are paved, as far as I've learned from the DARPA challenge. And so you can drive these, look at the right-hand side, these huge, this robot here probably weighs about 300, 400 pounds. So you can drive these regular tired robots through these mines. They're doing huge compute on board. And these legged robots and the quadcopters, things like that. You know, there's a few issues here. Landmarks and lighting, those don't exist in real mines that we want to be in. There's none in there because humans can't go in there. Why do we need robots? Humans can't go in. Ground robots aren't going to work. Any of you that have been in any of this stuff know that it's just too complex to really get through there, that you're not going to have a robot that works in the lab work out there. Limited endurance for the quadcopters and things like that. And then we looked at blimps last year. I don't know if you remember the talk, but we basically had an inverted raft blimp type platform. But you can only get about 100 grams of payload on a blimp that size that they're showing. And I don't know, 100 grams is pretty small. You can't even hold a flashlight for that. And you're going to go in a dark mine. I don't think that's going to work. But they've got a long way to go. And so what we've come up with, and there's the raft that we had last year, but is a couple of options. On the right is the floating quad prototype that we had. So take the quadcopter and put it on some pontoons. We've gotten almost an hour out of this platform driving it through mine environments and through the lab. And then this last year, we've been really working on basically a modified RC car. And this really looks like this guy here. So there's the two that went into the Gold King. You got a four-wheel on the left, and the front is our primary platform, which is a six-wheel drive vehicle there on the right. We've got 1, 2, 3, 4, 6 cameras on there, big computer up front, FPV, first-person viewer system. And you guys saw that one operating yesterday. I will say this is a little proprietary. We do have some patents pending on this. So just kind of keep that in the back of your mind as we move through here. We're running night vision cameras, run cams, GoPros, and some other Intel cameras to get all of our data, doing full 3D reconstructions on the stuff we get out. And this is a video that Jeff put together there. I want to show you that kind of tells us about the last year of the work that we've done. And I'm going to actually pull this up because we've covered a little bit of the background here. So I'll speed this up a little bit into our stuff. Oh. So here's kind of what the Gold King starts to look like there. Oh, come on. And here's the vehicle running through. You can see we're zipping over that water. That water is probably about a little over a foot deep, but we're just paddling right on top of that water. We climbed up over that rock outcropping there on the right-hand side. And we were able to navigate a couple 100 feet back into the Gold King mine with this platform. And it should bring out some data here. Let's see. Oops, that was a different, let's see. Come on. There we go. So here's a view of the crawler. You saw it working on the water there. Here it is coming up the side, showing you a little bit of how it moves through moves across this terrain. We did actually control it at first to do a demonstration to validate that the technology was there. We're building up the autonomy stack to run this autonomously through there. But right now we're sending all the vision data out because the probability of losing this guy in the mine is pretty high. I estimated just over 95%. So 95 out of 100 times we'll lose it. We did some testing inside a mock mine over the winter while things were closed, which gave us some really good data, gave us an idea of what we were, how we're going to build the 3D reconstructions. And here's this guy here. We've got a big Phoenix flashlight on the bottom, the Intel RealSense stereo pair and depth cameras there, a stereo GoPro, and our FPV cameras there in the back. So we're kitted out with high quality cameras for data collection. Here's a quick view of us running through. We've got a couple of clips here. But as you see, we actually controlled about 140 feet back. I think we went a little bit further than that, but that's a conservative estimate. And then in the 3D reconstruction, what you can see is just after we pull the vehicle out, we can actually build up a model like this, which shows you the inside of the mine. And so you can actually walk right through that mine. The other nice thing about that is we can pull that into CAD and we can make all the volumetric measurements, size measurements, and everything else like that. So special thanks to all the sponsors that supported this work. We saw this guy running, so that's a little bit of a detailed version, another view of what us running through the mine there. And I think I'm a little short on time, so I'll come back to this side. I'll thank you very much for your time today. And if you have any questions, I'll be happy to address those if I've got a couple of minutes here.
Thank you again. That's so fantastic. We'll take questions.
And I'll have to admit, I'm not going to be able to hear very well. So if Jeff could relay those or something, that'd be great.
Yes, actually on board in the Intel RealSense cameras that we have mounted on there is an internal unit recording accelerometer data on board. So we do have that for one version.
You have plans to install multi-spectral imaging of the robot so you can look at the geology as you're where the acid is.
At the current point, we only have the regular infrared cameras and RGB cameras, but I see no reason as to why we do have that.
Yeah, the vehicle itself is really just a pickup truck, so you can throw anything on it that you want. Our payload goes up to almost 4 kilograms.
It's actually 6.
Excellent. Jeffrey will be around for questions, and then maybe Ryan gets done completing secret missions and hanging out with 007Q in Oxford. He'll be back and do more demonstrations as well. And I gotta say, Ryan, thank you for taking the challenge. I said we want to see Big Ben in the background. Bam.
Thank you so much for your time, everyone. I really appreciate you bearing through a ported-in presentation and through all the technical difficulties. So thanks so much. Have a wonderful day up there. Really enjoyed it. I'm sorry I missed you guys this year. Hope to be back and talk with Jeff if you have any questions offline, or feel free to email me. Jeff's got my email address. You can rally up with that. And thank you so much, Marcy, for putting this wonderful event together.
Thank you.